In this video, we're going to be doing 10 MCQ problems for AP Physics 1 Unit 3 Work, Energy, and Power. If you want to follow along, you can go into the description and download this PDF and complete these yourself, or you can continue watching. So we have a cart of mass m that moves along a horizontal track. We have a horizontal force Fx is applied to the cart as it moves from x equals to 0, which is the starting position, all the way to x is equal to 8. The variable force is going to be shown on this position versus time graph. So we are asked to find the net work that is done on the applied force from x is equal to 0 all the way to x is equal to 8.0 meters. We are also given that the cart begins at x is equal to 0 with a speed of v initial, and this track is frictionless, which means that the coefficient of friction is equal to 0, so we have conservation of energy. What can we do here? Well, in order to find the net work that is on this object, we can look at the area under the force versus x graph, because work is equal to F times displacement times cosine of the angle theta. So you're going to find the area that is underneath, aka all of this. This is underneath the graph. Basically what we're looking at is this line that we have created on this position versus time graph. We're looking at the area between that line to the positive x-axis. So we can see that from 0 to 2, we have work 1. This is going to be our total work. We're going to call this work 1. We'll call this work 2, and we'll call this work 3. We have work 4. So after this, let's just add these up. Work 1 is going to be 1/2 times 2 times 8. And that is going to equal to 8 joules. So this over here. And we are going to have for work 2, 2 times 8, which is going to be 16 joules. Then for our work 3, we are going to have 1/2 times 8 plus -4 times 2. And that's going to equal to 4 joules. And then we're going to have -4 times 2. That's going to be -8 joules. So this is going to give us, cancel that out, we have 20 joules for our net work that is done. So now we are asked to find the final speed at x is equal to 8.0 meters in terms of m and v. So for final speed, we have to look at our work energy theorem, which says that our net work that is done is equal to the change in kinetic energy. So we know our net work was 20. We have 1/2 mvf squared minus 1/2 mv initial squared. This is the same thing as 1/2 mvf squared is equal to 1/2 mv initial squared plus 20. So we can cancel out 1/2 and multiply by 2 for everything. So we get mvf squared is equal to mv initial squared plus 40. Then we have v initial, or vf squared, is equal to v initial squared plus 40 divided by m. We just divide everything here by m. Now we just are going to take the square root of both sides, and we have that this expression is equal to v initial squared plus 40 divided by m. So that is your answer for part B. For part C, we were asked, suppose the same force graph acts on a cart of mass 2m with the same initial speed v initial. Explain whether the final kinetic energy is greater than, less than, or equal to the original cart's final energy. So we still have that the work from the graph will be 20 joules. So the final kinetic energy is going to be an initial energy plus that original 20 we had. So kinetic energy final 1 for the first cart is 1/2 mv initial squared plus 20. And then for the 2m cart, we're going to have kf2 is equal to 1/2 times 2m times v initial squared plus 20. So you can cancel out that 2 there. You're going to have mv initial squared plus 20. So the 2m cart is going to have a greater kinetic energy because it started with a greater initial energy, greater K initial. So that is why KF for cart 2 is going to be greater than KF for cart 1. Now, we have the same external work added, but the heavier cart is going to have more kinetic energy if we have the same V and we have a different M. Now, we have a block of mass M starts from rest at height h on a frictionless ramp and slides down. At the bottom, it compresses a horizontal spring of spring constant K on a frictionless surface, and the spring is initially going to be relaxed. So we are asked to define a system for which the mechanical energy is conserved from release to maximum spring compression. State which objects are inside of the system. So for our mass, it's actually going to have the spring on this side. And we can define our system as the block, the earth, and the spring. The block is going to be your mass M, and we have this way so that we can have our earth. That means that we can have a UG. We can have a kinetic energy, and we can also have a spring potential energy, because UG is when you have some gravitational energy, potential, relative to another object. Spring means we have to have a spring, and kinetic, we are going to have that moving block that is going to have velocity. So now for our second question, we're asked to derive the maximum compression X max of our spring. So if you remember over here, when we're at the very top, our energy is all going to be gravitational, and then when we're down here, once this reaches the bottom here, your energy is going to be all kinetic. And when you're all the way compressed to an X max, your energy is going to be US, because you're going to have the maximum spring compression. So at a very second, you're going to have your velocity equal to 0, and you're momentarily going to be at rest because you're going to be changing from going in a positive direction to a negative direction, reversing your direction to go back towards equilibrium after you've compressed that spring. So we can write out our energy equation. We are going to have, again, for part B, energy initial is equal to mgh at the top when you're at height h, and then at X max compression, you have your kinetic energy is equal to 0, and your final energy is equal to 1/2 kx squared max, aka just your all potential energy. So by conservation of energy, we can set our initial equal to our final. You're going to have mgh is equal to 1/2 kx maximum squared. You can multiply both sides by 2, and you have 2 mgh is equal to kx squared max. So then you can just divide both sides by k. You get that x squared max is equal to 2 mgh over k. You take the square root of both sides, and you get that x maximum is equal to this expression here. So that is your X max. Now for our next part, we are asked if the block is released from a height of 4h instead, determine the new maximum compression in terms of X max. So for part C, we're going to be adjusting our height. So we go from h all the way to 4h. So our new X max, we are going to have the exact same equation, 2mg, except we now have 4h instead of a normal h, divided by k. So we can see that if you have your 4, you can just take that 4 out. That's just going to be root of 2. And you still have 2mgh over k. So you can see that this was our original component, correct? That was this original component here. So you can just rewrite your X max as being twice that of your X max original. Now we are asked, explain why the normal force does 0 work even though it is necessary for the block's motion along the ramp. Well, we have to remember that when our block is on the ramp, it is going to have the normal force that's perpendicular to the point of contact, and that is a vertical force. and you have your force of gravity acting at the center of mass, pulling it down. These forces are going to be in your vertical direction. Your Fy is equal to ma. However, you have zero acceleration in the vertical direction. So your summation of forces in the vertical direction is equal to 0. And these forces only prevent the block from going through the surface. It doesn't move anything in the horizontal direction because your vertical and horizontal forces are completely separate from one another. So if you have for D, Fn does work equals to 0 because work is equal to also force displacement cosine of the angle. So we know that the force of normal is going to be perpendicular to the point of contact. That's 90 degrees. So we have cosine 90 degrees. And our force is normal force times D. So when you have cosine of 90 degrees, you have an x position of 0. So this whole entire thing becomes 0 times normal D. So work done is equal to 0 from the normal force. So this makes sense because the normal force, it changes your direction of motion, but it actually does no work. Because its displacement is going to be perpendicular to it. It's perpendicular to displacement. So you can imagine as the block is sliding down the ramp also, you have your block here, you have your normal force here. Your displacement is going to be in this direction, your displacement. So that angle between the two vectors is 90 degrees. Same here, you have your delta x, your displacement, you're going on the track, you're moving. As you get displaced, that angle is 90 degrees, so it does no work. Because when you do work on something, you have to exert a force that is in the same direction as your displacement. It has to be in the same direction as where you end up actually moving. So now we have for question 3, a block of mass m starts at rest at a height h on a frictionless curved track, and then after it reaches the bottom, it enters a rough horizontal section with a length d with the coefficient of friction mu k. It then reaches a frictionless spring at spring constant k, and then it compresses it. We want to derive an expression for the block speed immediately after leaving the rough surface. So we actually have the presence of mu here. Therefore, we can think up here. We know we have just ug, which is equal to mgh, and we also have frictional force. Frictional force is going to do work. So that is your force times displacement, and your frictional force is mu k times n. So when you're here down here, you have normal force acting up and mg acting down. So Fn is equal to mg because summation of forces in y is equal to 0. Fn is up and mg is down. So Fn is equal to mg. Now, what else? We know we can set up our energy equation. Our initial energy is equal to the final. So you just have kf plus uf is equal to k initial plus u initial plus work done by a non-conservative force, aka something that is going to be degrading energy. And it doesn't matter whether you put it on the left or the right side, your non-conservative force. It just depends on your system, and you just have to eventually remove that from your system because it's going to take the energy out of what we have defined as the constraints and bounds of our system. We have 1/2 mv squared, and this is going to be equal to mgh minus mu k mgd. So after this, we can divide everything by our just mass, and we have 1/2 v squared is equal to gh minus mu k g times d. After this, we'll multiply everything by 2, and that cancels out. You just have that velocity squared is equal to v squared is equal to 2g h minus mu k times d, and v is equal to the square root of that, 2g h minus mu k times d. So for our next question, we are asked to find the maximum spring compression x max. So if we have our rough section, or after the rough section, that means that we are no longer in X max because that's when we finally encounter our spring. So by the time we're at this point, we are going to be at our maximum displacement from the equilibrium, and that means that we have all of our energy equal to spring potential energy. So that kinetic energy that we have from sliding down here, that is going to be mv squared, and that's going to equal to all of the spring energy, 1/2 kx squared max. So now we actually have an expression for v squared over here. You can take this and just substitute it into v squared here to make things simpler. You have 1/2 2g because this 2 cancels out there, and you can multiply everything by 2. So then x max is equal to, dividing both sides by k, you have so that is your expression for x maximum in this problem. Now for our next question, we are asked to determine the condition h, d, and mu k for the block to reach the spring at all. Okay, so in order for us to reach the spring, that means that the block must have kinetic energy, positive kinetic energy, or kinetic energy equal to 0 after you are at the rough section. So if you are at a positive kinetic energy, then you have enough energy to continue moving at a velocity and compressing the spring, and maybe you'd reach your maximum x max, who knows. But if you are at k is equal to 0, that means you would just get into contact with the spring at least finally. Now that means that in order to have a kinetic energy, you have to have your mgh minus mu k mg times d, that all has to be greater than 0. So then if we just divide everything by mg here, we can cancel out those. We just get that our height minus mu k times d has to be something that's greater than 0, aka the height has to be greater than mu k times d at minimum. So now on the energy bar chart, identify which energy storage decreases and which energy transfers account for the missing mechanical energy. So if we were to draw our bar chart right here, for part D, we have UG, we have US, and we have kinetic energy. So, and we can also make one for our final. So in the beginning, you have gravitational. Let's make this like 5. And then in the end, you are going to have some of it become kinetic energy. Let's say when we are at the bottom a bit. So we're going to have kinetic energy and E thermal. So this is when you're before the spring. Your E thermal is going to take some of that energy away because of the friction section that you were just in. So E thermal has to increase. The friction is non-conservative and it removed the mechanical energy from the block earth spring system. Now a motor pulls a crate of mass m up a ramp of angle theta at constant v. The coefficient of friction between the crate and the ramp is mu k. The rope is parallel to the ramp. So we have a incline actually, so is parallel to the rope. This is your force applied. That's your M. So we want to find the tension in the rope. Okay, let's actually start with labeling our forces that we have on this diagram. Downward, we have mg, and perpendicular, we have mg cosine theta. Parallel, we have mg sine of theta. This is our theta, that's our opposite side, and hypotenuse is the mg. And then adjacent is that perpendicular part, and then the hypotenuse is your mg, which we know. So then what else do we have? We have a normal force that's acting upward, and the force of tension is going to be pulling the object this way. So how do we get tension? Well, we are going to say that we have friction that is opposing our motion as well, because we have a coefficient of friction. So this is going to be at the point of contact, we have Fk, force of friction, is equal to mu k times the normal force. So if you have a constant speed v, this means that your v is staying the same, correct? So if you have the same v, your delta v over t is equal to 0, and that's equal to your acceleration, so you have no acceleration. So now let's think about our summation of our forces in our x direction. This is what we have to analyze, because in the vertical direction it's not going through the ramp, so that means that the vertical forces are going to be balanced as 0. So Fx is equal to mass times acceleration. Your tension force is pulling up the ramp. Mg sine theta, that component of gravity, is going to be pulling down the ramp. And then mu k times mg cosine of theta, that is also going to be pulling down the ramp as well, our frictional force, which is opposing our direction of motion. That's equal to 0. So then you're just going to isolate tension. You have mg sine of theta plus mu k mg cosine of theta. So that is your tension. You could factor out mg as well. So your tension is equal to mg times sine of your angle theta plus mu k times cosine of your angle theta. So for our next question, we are asked to derive the power output of the motor while the crate moves at a constant speed. So the formula for power is equal to the force that you exert times v. So in this case scenario, your force is going to be the force of tension, which is v. So then that's going to be your tension, which we found is over here. We can take tension here and multiply all of that by v. So that is going to be your answer. Now for our next question, we are told that the motor has a maximum power of Pmax. Derive the maximum constant speed that the crate can have while still moving up the ramp. So in order to keep going up the ramp, our maximum power is equal to mg Vmax, which we had this equation. This is just the equation from part B, plus mu k cosine theta. So then you're just solving for Vmax basically. Then you just have your maximum power is equal to mg sine of the angle theta plus mu k times cosine of the angle theta. So for part D, we're asked, why does the kinetic energy not change even though the motor does a positive work? Well, the reason is because our work is equal to change in kinetic energy, and that is equal to 0. So the motor does a positive work. However, we know that our friction, work done by friction, this is going to be doing a negative work. And also the work done by gravity, this is going to do a negative work as well. So just because this motor does a positive work doesn't mean that the other forces that are going to be doing work don't do anything at all, that they cancel out. No. So we have to look at the fact that we have different works that are being done. We have work done by the motor, work done by gravity, and work done by friction. This is equal to 0. So the kinetic energy is not going to change of our cart, because when you sum all of these up, it's still going to equal to 0. So the positive work that we have from the motor is exactly going to be canceled by that of the negative work from gravity and from friction. So we have a 2.0 kilogram object that is moving in a straight line. Its speed changes from 3.0 meters per second to 7.0 meters per second while it travels 5.0 meters. The net force on the object is not going to be constant. Let's write down what we have. So we're gonna use the work energy theorem, which says that the net work is equal to delta K. And we have a initial of 3.0. So this is going to, if you plug this in your calculator, you get 49 minus 9, and you would have 40 joules for part A. Now we are asked to find the average net work over the displacement. Well, when you have net work, you are going to have to look at average. So you still have work is equal to your force times your displacement, but in this case scenario, instead of just force, this is going to be your average force. So you still have delta x. And we know that it's going to be moving in a straight line. We know that this angle is usually cosine theta, but we know that this is just going to be 1 in this case scenario because they're going to be on each other. So we have work done was 40 from our last question, and we have our force average. We know we moved by 5.0 meters, right? So then the force average is equal to 8.0 newtons. Yeah. So explain why the average net force is not necessarily equal to the net force at the midpoint of the motion. Well, because when you have average force, that is when you are looking at the area under the force versus time graph. So force, time, that's the area underneath. However, when you have the force at a midpoint, this is going to be just one value, aka like in the midpoint right here. So that means that these are only for special cases, and they would only be equal if you had, for example, you had constant force where you have just a line, so then that would be equal to the average. Or if you have a symmetric linear function, which I guess, well, it's usually just going to be a line. So that means that for this answer though, your F average is not equal to your F middle in general. So a student claims that the acceleration must be constant because the displacement and the initial and final speeds are known. Explain the error in the student's reasoning. Okay, this student is wrong because we know that we have the kinematics equation Vf squared is equal to V initial squared plus 2 times acceleration delta x. This is only when you have a constant acceleration. Constant acceleration means kinematics equations apply. So if in the problem it says that you have that acceleration is not going to be constant, then F net is equal to ma. And if the force is not constant, therefore acceleration is not constant, obviously, because we can see that they're directly proportional to one another. So work energy can find the total work without knowing whether the acceleration was constant. We can still use work energy. Now, block of mass M is attached to a vertical spring of spring constant K. The spring's unstretched length is L initial. The block is lowered until it hangs at equilibrium, and then the block is pulled downward an additional distance A and released from rest. Derive the distance that the spring stretches from its unstretched length when the block hangs at equilibrium. So when you are at, for question A, when you're at EQM length, you have to remember that the force of gravity, it's not going to change your period of your spring. It's just going to change, or it's just going to shift your period. That's it. Because period isn't related to your amplitude. So At your equilibrium, though, your summation of your forces is equal to 0 because you have 0 acceleration, because your V is going to be at your maximum, so you have K max. And also your US is going to equal to 0 because your displacement from equilibrium is equal to 0. So we can just say that on our spring, let's just draw this out. You are currently at your EQM. This is your spring. Well, you're going to have an upward spring force. If you stretch it, it's at equilibrium. So you have KX EQ, and you have your weight force that is going to be down. So minus mg is equal to 0. That's equal to mg. So that's equal to mg over k. Now we are asked what, taking the gravitational potential energy, spring potential energy, and kinetic energy into account, derive the speed of the block as it passes through the equilibrium position after being released from rest at an amplitude A where we stretched it. So if you have displacement from equilibrium, your vertical spring behaves like simple harmonic motion. And when you are at the bottom release point, what this means is you just displace your spring by a little bit, aka you pulled it down like to here. So now it was like this, for example. Pulled it down here, and then this was an amplitude A displacement. So you stretched it all the way to its max, x max. X max is squared, so it ends up not mattering with this up or down. So you at equilibrium though, U is equal to 0 again, KF is 1/2 mv maximum squared. So we have conservation of energy. We set them equal to each other. You have 1/2 mv squared. 1/2 ka squared is equal to mv squared, and you have v squared is equal to ka squared over m. So v is equal to the root of a times k over m. Now, for part C, we're asked, explain why the motion can be analyzed using energy even though gravity does work during the motion. Well, that's because your force of gravity is going to be a conservative force if our system is defined as our block plus the earth plus our spring, because our gravitational energy, our Fg, is going to be stored as gravitational potential energy, mgy, from where we define y as our height. So your mechanical energy is still going to be conserved. So conservative forces do work without destroying mechanical energy from our system. Now we are asked, if the mass is replaced by 4m and the extra pole distance a amplitude a is used, determine whether the speed at the equilibrium is greater than, less than, or equal to the original speed and justify with an equation. So originally we have that v is equal to the a times k over m. So now in your new scenario, you have just 4m. You have v prime is equal to amplitude over k divided by 4m. You can take that 4 out, and you get 1/2 times the exact same equation you had earlier, k over m. So you can see the only thing that changed was you scaled by a factor of 1/2. So v prime in comparison to just v is just 1/2 v. So we can see that your v decrease, it's going to be less. So that's because we increase the mass. And increasing the mass, it's going to lower the spring oscillators V max for the same amplitude that you displace it from equilibrium.